Okay. Good afternoon, dear colleagues, esteemed lecturers Wael and Guillaume, dear colleague and friend Michel Abou Jdid, President of the ASCE Committee in Lebanon. For the past 2 years, there has been a collaborative effort between the first branch of civil consultant engineers and the ASCE Lebanon section to organize research lectures on pertinent scientific topics within the field of civil engineering. These sessions aim to not only our fellow professionals, but also aid in the enhancement of their professional expertise. In the previous year, we successfully conducted 5 seminars over a span of 5 months, with the intention of maintaining a monthly schedule. However, due to unforeseen circumstances, this initiative was temporarily halted. Today, to announce its revival. It's our belief that the platform provided by the OEA, Order of Engineers and Architects, serves as the ideal forum for such endeavor. In the previous seminars, we addressed several topics, mostly related to structural engineering, with some branching out into other specialties within civil engineering umbrella. As for today's seminar, I extend a warm welcome to our colleague Michel Abou Jdid, who will be leading today's session, and for sure, I express my gratitude to our colleagues and lecturers, Wael and Guillaume, for their diligent effort in preparing for this webinar, which focuses on material widely utilized in industrial and commercial engineering sectors. As civil engineers, most of our usage revolves around structural material, such as concrete, steel, asphalt, rocks, and soil. And regarding plastic, its utilization touches on some lightweight structural elements. If we return to artificial intelligence, AI, in our research question about the possibility of adopting plastic as a structural element, the answer comes as yes, with numerous applications, for example, in the field of construction, for structural elements such as roofing, wall panels, windows, and doors. In the field of aerospace, lightweight and durable plastic are used in aircraft components such as interior panel and structural support. In the field of automotive, in the other fields also, in the marine field, plastic are used in both construction for hulls, decks, and other structural elements due to their resistance to corrosion and water absorption. As for the field of sport equipment, also plastic are used in the construction of sporting items like tennis racket, golf clubs, and bicycle frames, providing strength and flexibility. And we cannot forget the field of infrastructure, where plastic can be used in infrastructure projects, pipelines, and retaining walls. What we are discussing today is highlighting the role and potential use of specialized type of plastic, which has been elaborated by 3D printing as a fundamental material in the structure, which our lecturers will guide us through. On the other hand, it may be useful to touch the subject from a different perspective, based on the principle that if plastic is left to natural degradation conditions, it's very resistant to natural degradation processes. However, if we create industrial conditions for transformation and decomposition, plastic may be easier to decompose and recycle than other structural materials. Hence, the question arises, will finding the possibility of plastic and structural elements increase the possibility of working on developing its recycling and disposal as non-negligible waste, those having both structural and environmental benefits? I return and welcome those present with us in this webinar and through Facebook, and I ask my friend and my colleague, Michel, to take on this seminar.
Thank you, Dr. Joseph. Good evening, everyone, and welcome to another joint webinar between the ASCE Lebanon section and the Order of Engineers and Architects in Beirut. My name is Michel Bouchdid, and I'm the president of the ASCE Lebanon section. And my co-host is Dr. Joseph Mshaileh, and he's the president of the OEA First Branch Civil Engineering Consultants. I would like to start by thanking our speakers, architect Guillaume Credos and civil engineer Wael Kayali for being with us today to present this webinar, and Dr. Joseph Mshaileh for hosting us here tonight at the OEA. Today's presentation is titled, Is Plastic a Structural Material? And is divided into two parts. The first part relates to the structural strength of plastic and will be presented by Wael. And the second part is associated with the architectural use of plastics in construction projects and will be presented by Guillaume. Guillaume is the CEO of Bits to Atom, a practice that explores the potential of digital manufacturing to extend the capacity of crafts in architecture and design. Wael is the CEO of engineering consultancy WKO, which focuses design of roads, infrastructure, and concrete and steel, in addition to the extensive experience and the rehabilitation and retrofitting of deteriorated and damaged buildings. I would like to ask the audience to type their questions in the comment section, and we will address them at the end of the presentation. Without further delay, I will now give the floor to
Now, first of all, this webinar is about one major question. Are plastics structural materials or not? In my opinion, yes, they are. Simply because they are good materials, strong materials, although they have some disadvantages that we should address. But in general, yes, they are. Now, I cannot present this unless my friend Guillaume would present you what he is doing in Bits and Atoms and how he is designing plastic structures intuitively, without calculations, without engineering, going into engineering practice. However, this intuition will end up with a theory of proper theory of plastics, of structural plastics that can be utilized anywhere for plastics, with his work and with other works. That's why I represent for you Mr. Guillaume Corridos, that will talk to you about the architectural part of plastics and the reuse. Please.
Wonderful. Thank you, Wael. Okay. So we'll switch documents. 1 second. Okay, we'll start on page 1. Not 32, or I guess I can start that. So I will first introduce the practice in general, because we are a research place where we work on materials. Today, of course, the focus will be on recycled plastic. So I'll be able to switch back to start, sorry, a bit quickly. Where is the document open there? So here we are. I'm directing two practice. One is located in France, the other one in... Ah, wonderful. So much practical. So one is located in Lebanon, it's Bits to Atoms, where we work on digital fabrication, and the other one is Post-Industrial Crafts, which is located in France. So I'm an architect, I make buildings, but I also make robots. This one on the second floor, enormously. And then I also house old robots from automotive factories, and then I transfer them into large 3D printer with which we do furnitures, which we sell. So this has been a long journey. This is about the last 10 years, from creating my first own 3D printer 10 years ago, and then doing first furniture, then buying my first robot, transforming it, etc., until we reached a point whereby from furniture, we moved gently toward the architecture scale. So this has been done through several machines, through several systems. So we first had the first 3D printer, built our first robot, get our first robot, and make our first 3D printing robot to create various structural systems using various materials, from recycled paper to wood, concrete, recycled aluminum, recycled plastic, to work first at furniture level. That's where how we do our small prototype, because it's relatively not as costly as doing architecture. And then we either use our architecture project as a reason to try and to experiment with the material and the process that we are setting up with our robots, or we do ourselves our own research. So we've always been very much into structure. So 3D printing with plastic, with a laser printer, we've been creating this construction toy, which allows kids to play with wood pencils in order to build about anything. So you see here, that's how I became a bit an engineer, because I designed an engine which works with a spring, but I had to do everything in order to make it. So it was quite fun. And for an architect, to do a bit of engineering. And we have our machines, so we get them used. We build the extruder, and we build the controller and the codes to make them work. And with this, we manage to produce some stuff. So what we do is that we collect from the environment bottles, which are made out of polycarbonate. Once they get a bit too dirty, they are trashed away. So we recycle them, we crush them, and from that crushed material, we use it in our robot in order to produce furniture. So that was the first move. You can see the first chair we've ever printed. That was like 4 years ago with the machine, with our first machine. And then we moved on, and we recycling more materials. Now we're recycling car headlights because it's a very good polycarbonate, which is quite transparent, which allows us to play with color. And we started gently in our furniture to start to make structures, because indeed, you can see that those parts are 3D printed, and but also the center one, the structure itself of this large lamp, is also 3D printed with an assembly, a bit like you would assemble wood somehow. Still a very basic assembly, but you can see some triangles which are there for structure strength, which are carrying this structure. So we got our first small contracts. This one was for Hermes in Dubai, and it was a bit at little architecture, very little architecture scale, but we only did those panels, in fact. So the structure is still wood structure on which our are mounted, which was not really quite interesting, but that was the first move. And from that crushed material, those bottles, we started to print beams in order with you see, we prepare a hole for a connection, so we could do some assemblies, and we could start to be structured. So the first about structure was to have a first layer of triangles, and to have tetrahedron, and then to have hexagon, and create a space mesh in order to get this material, which is very flexible, and compared to concrete or steel or whatever, you're facing a very weak material compared to what we used to. So you need to put more brain into it and more geometry in order to get the strength you need. And you need to give it also more volume. So you could see the first attempt, the first prototype we did of a space frame. I'm sitting on it because you see that obviously the strength is directly in question as we use polycarbonate, which has a lot of qualities, but still, when you start to make it, you see this one here, it's bending under half of my weight. I mean, so it's already enough. But when it's all together and the pressure is applied directly on the point, you can still cross some good distance. And because you've got a great height, thanks to this structure, the ratio weight of the structure compared to its capacity is interesting. And the good thing is that as this design is entirely coded, we can have, our code takes the geometry, the base geometry, and send it directly to the robot. We can have extremely complicated structures with every beam and every triangle to be unique. The complexity of it is not a problem for us because we don't see it. It's all managed by the code that sends it directly to the robot. We just have to in order and then assemble them. And then we are going through without having to know any number, any angle into this kind of structure. You see, it could make things complex. We still didn't reach there, but we started to reach some elements. I mean, so the recycled plastic has a various quality and comes from various parts because we have to gather it a bit everywhere in Lebanon. It's not completely easy to do. But you see, we start to have some structural answer to this thing. As well was noted, it's not really calculated. It's more we do it and then we jump on it to see if it's strong enough. That's a bit the technique. But somehow it's a kind of a valid technique when you have a big workshop and you're able to print like this. It's not really a problem. You learn a lot more by doing it just by trying to simulate it. And somehow it was useful. We use it to answer to competition in France. And now this structure is a permanent structure in France, in the courtyard of a castle. It creates a labyrinth, which is dismantled and rearticulated in order to host 3 festivals every year. And during the festival, when in the empty time, another shape of labyrinth is created, doing placemaking inside of the large courtyard. One of the good things is that it froze one morning we were installing, but polycarbonate is also used for the helmet of the astronaut at -250 because it still can be flexible and resistant into these temperatures. So that's practical. That was a freezing morning in Britain in winter when we installed the thing. The contrast between this very weird structure made from about 30,000 bottles were recycled with the old stone was quite interesting. So that was part of the success of this installation. We did it again with the headlights in Milan to be a support for an exhibition. So this time we get a lot of transparency by the change of material. We pushed it a little bit further by really making it the center of the attraction when we answered to the competition by the Royal Commission in Dubai to create an attraction into public space in order to get people out of their home post-corona so that they would do some sport and have some communication. And we proposed to build a large beam spanning 40 meters long at 3.5 meters high that would be made completely out of recycled plastic and that would hold people that would swing under it. And this time, this beam was completely made out of recycled plastic. So we had to make every segment also a beam itself with reinforcement in order to get the strength needed. But somehow we managed to get a structure that was really sturdy with almost no flex, very, very strong. All the moment, the resonance or whatever, it worked very well. The thing that we had to do in order to reach this is that we had to insert a metal flange inside of the print while we were printing. So the flange would be stuck in the plastic. We did some traction test and it needs above 1.5 tons in order to take it out. It doesn't get out. In fact, the plastic breaks behind it. And this allowed us to connect many points on one screw. And because with plastic, we needed to make it a lot larger. And you need to enlarge all the dimensions because your material is several times weaker. So if you get many beams with that enlargement, you get a giant knot and you cannot make it through. So this was a good solution. And you see, we did everything in recycled plastic. I mean, from the ladder things, the rings, well, of course, the seats and stuff, etc., but also the seats for the swings. It was assembled in overnight over there on the show because in kind of those kind of conditions that you get when you're inside of a festival. With a great success, and it became it was just a test, and it became a permanent installation, which is in a park in Dubai. This was also a bit more pushed one in Brisbane, in Australia, competition that we built here in Lebanon. This is the test assembly. It's the architecture student that built it again in Brisbane, next to the Brisbane River, for an art festival. And then so the same system of beams. You see, I'm standing on it, so it's always a bit the proof of the idea, because of course, as we don't calculate it before, we do it and then we test it, and then that's how we prove the thing, and then we assemble it. But we use shapes which have a lot of intelligence, and we use more instead of doing a big slab a bit stupidly. I mean, like this. Here we have to use very intelligent shape that would compensate for the weakness of the material. So the proportion of strength is reduced. The proportion of intelligence into the shape is like very much enlarged. That's why we get this kind of shapes. So so it could carry the full office. I mean, like, so 25% on that structure. It had very good property, very good resistance. Overall, very lightweight, and very interesting to assemble. So this made us think further. Instead of thinking with segments, we started to work more as cells. So it's assemblies of cells which are printed separately, and that are kept together in order to create larger elements. So we won a small competition for a gate for ISRA, for Saudi Arabia, for an event. And here you can see the 3D printed scale positioned. So you can see here every element is numbered. I just have a very simple facet model, which is almost like only 2D, and then the codes take it, will make the 3D of every element separately, and then we'd make code for the robot for every element separately. We'd code and play it on the robot. We would just number it with a stamp while the plastic is still a bit soft when it's printed, and then we will assemble it following the diagram which are provided by the code as well. So it's direct digital manufacturing. It's quite interesting because with the amount of elements you have, which are almost all unique, you cannot really follow up or make construction drawing of this. So this is all solved by the code. So it's just me who creates the shape I want, and then I've got directly them printed somewhere. And in between, there's nothing. I mean, there's just the code, and now I can do many shapes using this code. So the logic is that, so you've got every element separated. They all have a stiffener on the side. So, and the stiffener click one into another. So you have a male stiffener and a female stiffener. And so this is how you make a system that resists to lateral forces. And then you've got connecting joints. It's very interesting because in this one, you've got many conditions. You've got 2, 3, 4, 5, 6 connection. And in fact, it's just a ring. And then you put everybody in tension and you pull them together. So you're sure that touching the next one. And that's how you create the full thing together. And you get it like it's a bit more like a fabric, but the overall shape is giving it also structure, and the thickness is creating it. The hatch that you see here printed are giving it also rigidity, and they are bracing. And we're using all this logic in order to get to a sufficient strength for the structure. And the last one is for a French perfumer. It's a pavilion, so it's very interesting. Instead of paying someone to make another stand, and a stand designer, they prefer to invest into someone who does research for architecture. And then they give us a subvention for our research, but we gave them a pavilion as a result of our research. So it's far more productive than doing a stand and then trashing it. So and indeed, they are sending it back to us so that we recycle it. So we will give it the plastic another shape for another time. So this was a 3D printed model, and this time we had to we had a condition which was quite more clear because we had only hexagons which were divided in 6 triangles. So we had connection with 6. we're on the limit of the structure. So we took the occasion to design connectors that would be made entirely from local recycled aluminum. You can see it could be open. It's a kind of a stuff, and it has two faces which are held together by one screw. And this is the one that we'll put into in the same way as I explained before. That would put together those cells, and that would connect those ribs, the stiffener, which will get one into another. And because of the code and how it's done, and the angle on the walls, then when you put them together, you will start to create the full shape of the pavilion. Here you can see the scale. You can see workers inside in yellow. And that's the scale of one triangle. So one triangle is about a meter. Of course, there's 190 triangles, and they are all unique. They all have different shape, but the average shape was about a meter. And that's how you lie inside of the structure. You could see like the hatch that we put this, that it would be continuous, and it would go through all the elements that are printed separately. But when they are reassembled, you can see there's a continuity of the structure, of the texture. And it's a bit like a river flowing through the shape. So you have a kind of a 2D shape and a 3D, which are merged together to create this intriguing object. So here, this was the first dry in a location away from the exhibition, because we had very little time to do the full assembly. We had a night to do it before the show. So we trained a team of Bangladeshi workers. We explained them the logic of the puzzle, and they all found it very fun, and they collaborated a lot, and they got very fast into doing it at the end. It was very, very interesting for us. They understood how this was conceived, and it was a very nice experience with the team to make this happen. And finally, it was built on place, and the perfumer to present his creation, which were all put very preciously on stands that we also 3D printed from the same material, which were lit from inside, giving all this reflection and giving all that quality to the product that was on top of every one of those elements, the few trees inside. And of course, on the limits, we had special conditions. I mean, you see here we are on an edge, so we have only 3 triangles. We still need to pull them all together, but we don't have anything on the outside limit because we cannot put any anchor on the ground in the exhibition space. The structure has to be self-contained and self-maintained. So in fact, we had, which was fitting very well inside of the female stiffeners on both triangle, and that was resisting to the pull from the 3 triangles, which were closely stayed together. Kind of connector that we had the right to put 1.6 centimeter into the ground, which was made out of. So we also created some connectors there in order to make sure the structure will not go away if any crowd movement would bump into it and take it away. So you see it's during the installation, during the night, we had to build it. And the latest one we did is trying to be a bit better, because this system has a problem. We drill through the plastic, and it's a weak material, and we're making it weaker. If you drill it through, so you create a hole, you remove some matter. If anything's gonna break, it would be where the hole passes. So I was trying to think of a way to keep those cells together without making any holes. So that's how I created another type of joint, which is made of also recycled aluminum and recycled plastic. The cells it's another cell system. You know, it's a very regular one. It's a carbon atom. So it means you've got 1 pentagon and 5 hexagons around it. They all have, this time, stiffeners which are towards the inside. And to keep them together, you've got 2 connectors, which are grippers. They have 3 fingers, and by 1 bar in the center, and they are put into compression. And the more you tighten the screw, the more the 3 cells are getting. And this way, you secure the assembly. and you don't have to make create any weakness by creating any holes into the system. So this has been assembled in France and will now be part of a scientific it's a museum in the of Saint-Étienne. This prototype. And that it will be the cool thing is that it's made from the car headlights. It has a lot of property with the sun and the light. It's quite interesting, and we're going to put some light inside because we have those two inward stiffeners which are creating a void at every member, and then we'll be able to pass some light inside of this. So you see, this is a connector in a close view, which is keeping those three elements together. So this time we also add only one condition, which was having three cells touching together because they're all hexagons or pentagons. Now you see the connector itself, to save some money and some material, has also stiffener and the same wall thickness all the way. Be sure we have the best result with the cast aluminum. And you can see the stiffener, which are also taking the efforts together to the screw. Here you can see a bit what's happening with the material. This natural sun, and that's how through the surface, which create a lot of refractions, a bit like a Fresnel lens, and that's what's happening when we're putting some light inside. It's quite fascinating, and so it's a very nice material. It's very rare to be able to build with this kind of property. One interesting thing is as we print those cells on the ground, we can also print anything at the same time, which means we could print the closed, we could print shelves, we can print table or benches, and they could be part of the assembly later on. So we could build on this, and we could add a lot of things as we build them, and they could be different. Here you see the test of a bench, of a chair, which are part of one hexagon and another hexagon, and that are assembled together with the same version of the design of the joint before we evolved it. So the next steps, we discuss a lot with artificial intelligence. It's very funky to throw stuff and to get stuff back, etc., and to discuss and to chat with those animals. And we do stuff. We see some stuff, we discuss stuff, and we do other ones. This is the last chair we did. We created a very funny code that makes airs. It prints in the air, and so some part of the print fall, and it creates a kind of a hairy surface on the back of this large armchair. And you see the material is almost glass-like there because we have very nice material. But in terms of architectures, we are looking at these kind of things coming from AI, and we are looking at this kind as well. And we are looking at this, and we are trying to see a bit how we could push forward this kind of shapes. We are quite attracted by those visions, by those dreams of AI, which react to the keyword we feed it through the prompt. And we think we foresee some ways of doing it, and could be the key to achieve these kind of things, which are quite attractive as an expression, like an architectural expression for an architect. So this would be the next steps. So I put the mic to Wiley.
Hello? As Guillaume said, he did a lot of structures intuitively. But from now on, we are going to talk about the structural properties of the plastics and other materials and compare it to other materials. Now, I will start by saying the availability of materials on the crust Earth are, as you see on the right side, it's oxygen, 47%, silicon, aluminum, iron, calcium, sodium, whatever. But the structural materials being really produced on Earth is first steel, which is around 1,500 million tons per year, which is huge. And let us say that plastics is the second material being produced, followed by aluminum, copper, and zinc, and whatever. So plastics are not rare materials. We have a lot of plastics in this country and around the world. Now, plastics, what are plastics? Plastics are synthetic materials or partially synthetic materials that are made of various organic polymers. Polymers, they contain carbon, hydrogen, oxygen, and organic matter. And they are always of a molecular weight of large kind. The molecules of the plastics are strong, but the bond between one molecule and the other is not. This is why are somehow flexible. Now, because the bond between different kinds of plastics from the atoms of the plastic unit, they are made of covalent bonds, while the bonds between one molecule and the other made of weak bonds like bonds, much weaker than the covalent bonds or atomic. Now, say that plastics, all plastics are polymers, but not all polymers are plastic. Now here I have an Ashby chart that will show us the strength of materials versus relative cost. As we can see that while plastics are here, of course, carbon steel is stronger. In the other Ashby chart, we can see the strength of a material versus the workable temperature, which is, let us say, we have here plastics in this area, and I have chosen this, which is carbonates, which is here, and nylon that are here, and we have polypropylene here. I highlighted these because they are the most important ones and other now polycarbonates are strong enough and they can take relatively they can work in relatively high temperature, high ambient temperature, not doesn't melt on this temperature, but it can be used without excessive elongation at this temperature. So if the ambient temperatures is up to 100 or even 120, still polycarbonates can work. Now, properties of some plastics. I made this chart to show the properties of some plastics. Now, polypropylene is around, have a density around 0.95, slightly less than water. And the modulus of elasticity, that's a Young modulus of elasticity, which is low, 1,300 megapascal, yield strength of 33 megapascal, and an ultimate strength of 40. These are average, not really exact, because all plastics have different grades, and they but polypropylene has a unique thing about its elongation. Some it breaks at about 8% only elongation, and sometimes it goes up to 600%. I mean, it will elongate very long before it breaks. This is because of different configuration. Now, polyethylene, we all know that polyethylene of high density, low or medium density. That's why the density is really changed. Now, the minimum modulus of elasticity is this, but the higher modulus of elasticity, I didn't show it here because it can go to and it's not yet fixed. And its elongation 100%. Now, polycarbonates are more polycarbonates are, their range is much smaller. That's why the density is around 1 time, plus or minus, there is a too much. And the modulus of elasticity, also depending on a lot of things, can vary. While yield strength also can vary, but you can see the difference is reasonable, not too. And its elongation is around 70% plus or minus. And the ultimate strength can go up to 80 megapascal, which seems high compared to the others. Nylons are not really used in real structures because nylons are used in flexible structures, more like bags, like tires, automobile tires. That's why nylons are into construction, but they can be used also in a certain. Now, the polyurethane, because polyurethane is a material that varies too much, really varies too much. It can be of very low density to a very, and it can have a modulus of elasticity between 30 and 2000, which is too much in range. And it's too high. It can go down to 2%, which is very low, to 950%, which is extremely high. Problem with polyurethane is that it's not really, there is a way to make it more stable and to control this, but when we can use it for waterproofing because it can elongate very much. And if we make it rigid, it will lose its strength. So we have a problem. But it is used very much for foams, and that I said it is used mainly for foams, not for real solid things. Maybe, but it can be used. Now, This is about polycarbonates. Polycarbonates, as we saw in the previous one, should be around evidence of E and E of around 500, 400, 2,000, 400, and the ultimate strength of 80 and the elongation of 7. We made a test in AUB actually, and this test showed very good results. We found that the ultimate strength that we got from a sample from Guillaume, that is 25 megapascal, which is very close to the 8 most of the references mentioned. And the yield strength was around 50. Now, if we to concrete, it's much stronger than concrete. It's around 3 times concrete, which makes us think that this material is really strong. It's stronger 3 times than concrete. What do you want? You have a problem that the modulus of elasticity is a problem. The modulus of elasticity of polycarbonates was found in our test to be 700 megapascal. Of concrete is around 21,000 megapascal. That's times 30 times too much. And this is the problem of plastics. All plastics have the problem of modulus of elasticity, not strength. Now, here it shows a machine, it's a Sharpie test machine that proves that this machine is for measuring the ability of impact to the load to impact of any material. A glass can be a very brittle material, can break easy. It will break easy with a small groove. Steel needs a bigger groove to break. Plastics actually proved that they can take really good impact, very strong in impact. Now, in plastic strength calculations, which is the most, all plastics are ordinary material that follow Hooke's law. That's definitely, we can say it without any reservation. The yield strength is usually well defined, and the ultimate strength is also. And we can, if we don't know it exactly, we can test it. And the usual procedure for stress calculation in classical materials such as steel, aluminum, wood, and any other are similar to the same thing. And the stress can be calculated using any formula of the formulas that you are using anytime. Stress load over area, and the moment is moment over the section modulus, and the moment of inertia is exactly the same like any other material. However, there are other things that we should take care of. For example, this is, I'd like to show you this. This is a simple example of a beam made of plastic, and I made it in the shape of a 3D print. But it doesn't have to be 3D printing. It can be molded as it is, or extruded, not only molded. Now, if we have a slab with the span of 3 meters to be constructed using polycarbonates, at 30 centimeters center, and we made the calculations. I found that the problem is that you can see and go through calculations. I think I have to go through the calculations, but the problem is the strength. You see, the modulus, section modulus was 145.7 centimeter cube, and the stress was something like 5.8 megapascal, while the ultimate strength, not the ultimate, the yield strength of this plastic is much higher than that, about 10 times that. So still, it didn't work. Why? Because of the deflection. Not any other reason. The deflection was 10.12 centimeters, which is that. So we have to increase the section until we reach 2.39, which is 1/125 of the span, which is still not very well, not very good, as we usually accept. However, for temporary structures, this is very good. For temporary structures, this is usually acceptable, but it's not acceptable for permanent structures. Slide shows one of the structures that Guillaume have just. It's the one done in Dubai, 60 meters, around 60 meters long. Sure, but this is the way it was done by robot. It's simply, and I'm sure we can do analysis just like any other structure we can. Now, the problem, good thing actually, not the problem, in plastics is that plastics can also be used as composite materials with other materials. Composite material is a sandwich panel which is made of a steel plate about millimeter from up and down, and we have a foam in between, polyurethane foam. As we mentioned minutes ago, polyurethane can be used as a foam. The problem with this kind of structures is that the mode of failure is different than the mode of failures of concrete and steel. Most of the will fail in tension or compression, but this one, the common failure is face wrinkling and shear, not moment. Why? Because, well, we'll talk about it. I put it on purpose simply to show that this picture, wood, pieces of wood put on the steel, to create a stair, but it's not actually. This is done by very thin plastic plastic that looks like wood and filled with foam. This is it. Now, there are some examples where foam can be structural material, such as these prefabricated houses. frameless without any steel. You can create such thing or this shape or even this shape. Easy. Now I made an example of a sandwich panel of one story like this one, simply because it is very simple. And the connection is similar to this. This is not a steel frame. This is simply a flashing to protect the sandwich panel from water. This is not a steel frame. And here, the connection between the wall, which is also a sandwich panel, and the slab, which is also a sandwich panel, is simply a small angle of steel angle like full bent angle, nothing more. Now, let us see this. This example shows us a 4-meter span with a sandwich panel, and it worked for 20 centimeter in thickness. The face, the E, or the modulus of elasticity of the face, which is steel, is around 200,000, while the modulus of elasticity of the filling foam is around 1600 megapascal. However, this is the E of the what we call the solid, while the E of the foam material, usually it is proportional to the square root of the material percentage. So it's 95% air, void, and 5% material owned in this foam. And squared multiplied by this will end up with a very low modulus of elasticity. If we do this, and we take the shear, which is around, usually taken around E multiplied by around 1 minus Poisson's ratio, it will end up something like that. Now, whatever it is, most important thing is that the only thing we cannot oversee is that take the deflection. Deflection due to moment and bending is only 4.33 millimeter. While in concrete or in steel or in aluminum or in glass or in any other material, we don't usually consider deflection due to shear. But in foam, we cannot. Deflection due to shear turned out to be 9.29 millimeter, more than 2.5 times deflection due to bending. And this is unusual. So the total deflection was like that, and even this was not that good yet. But at the end, it worked. I will also continue. Also, the foam can be used, and walls can be used, also designed and analyzed like any other one, taking into account the moment and vertical load, but we cannot also see the deflection due to shear. And deflection due to shear will also, we have to add the long-term deflection, which will end up with bigger deflection than you. That's why this is the problem in walls. Now, plastics are good to build durable and recyclable material and reduce carbon fiber. And we can say that at the end that they are strong, durable, stylish, whatever reasonable cost. They are reasonable cost because they are recyclable, and they end up with greener environment and can be used in composite way. So plastics are actually structural materials, and I hope that you are convinced that they are structural materials. Thank you very much, and sorry for taking all this long time.
Thank you, Wael. Thank you, Guillaume. We're going to see if we had some questions now from our audience. If we can post the questions, please. Can we have another microphone, please? In the meantime, I have a couple of questions I would like to ask. Guillaume, you were mentioning the material that you use, such as the car barrels for your test samples. How many times can you reuse them? Because you mentioned you did them and then they send them back to you for one of the projects because they didn't need them anymore, so you're going to use them again. So how many times can you use these already recycled material?
We did the test in AUB laboratory for. We did it on one cycle. We didn't do it for many cycles. So, but what we do is that we kind of mark the material which have been recycled more than one time, and we use it for less demanding applications. So when we do lighting, when we do pots, this kind of thing, we always use that material. We know that we lose a bit of the material capacity. The good thing is that 3D printing, we're not taking material up to liquid. We're taking like just at the level where it's paste and gluey. And that's, we are just between liquid and solid somehow. And this thin frontier, that's where we print. If it was completely liquid, it would fall. If it was solid, it would not go through the machine. So somehow we are taking it to not to a very temperature, so the degradation is less. And also it's just passing through. It's not staying warm or hot for a long time. So normally the effect is not too hard. The problem that we have structurally is that unfortunately, on large objects, we print them, so there's a gradient of temperature inside of the object during the print. And this creates forces, inner stresses, because some parts have been shrinking while other ones have been put over. And we have sometimes curling into our parts, and we know that there are strong internal forces. Somehow it's a bit like they've been quenched. They've been to somehow hit them again. And this is what we are developing now. We are developing a kiln so we can, again, take the material to a temperature too high, just to release a bit those forces into the material in order to get elasticity again. So we know, same, it's more by experience. While was talking by intuition, there's also the culture of an architect to do things, and also experience. Indeed, we cannot really, I mean, we do a lot of experimentation and research. AUB did one time for free this test for us, but we could not do it like 10 times to know how many recycled and of that suite. It would be quite interesting, but we are a bit limited. We might get better at this because in France, we're getting actual funds for research. In Lebanon, we are left completely alone with nothing. And so we are not capable of sustaining the kind of thing. But in France, we get funds. So we also get interns from university and support. And really, one student can take this as a research. And then you can actually give us complete answers on this, which would be quite interesting. We would get a percentage of weakening by cycled, which would be really great. Yeah.
Exactly. So then we do know for sure that the properties are changing after recycling. And so the the final place of plastics is not, you know, they're eventually after a several cycles, they're going to end up in a landfill.
Yeah, unfortunately. So what we do is that we use 100% of recycled. We never use a gram of fresh plastic, so we don't participate into creating new plastic. And what we do is that most of the things we get it in a shape which is far more fragile than what we produce, because our minimum wall thickness is 12 millimeter. So we never make anything which is less than 12. And what we do is that we mark it with the type of plastic. And we don't put any adjuvant or anything. We do structure which are monoblock made from one material. When we do assemblies, you can just remove a screw and then you've got one pure element of plastic which you can recycle directly. We also put our name on it, because when we sell it, we say if you don't need it, if you give it back to us, we're responsible for it. We would continue recycling it, even if we downgrade the use of it. There's still many cycles into this, even if it becomes a pot or even if it becomes a tile. I mean, like to the last of the thing. So some of those structure, which are the furniture we do for furniture, those 12 millimeter, the shield of the CRS in France, which we like blocks, road blocks, I mean, are 5 millimeter. So it's already very hard to break. We are doing 12, so we do furniture that's going to last a long time. We foresee as the cars of the light of the cars, which are supposed to be okay under the sun outside for 30 years. We think that our furniture would do the same. So at least this plastic will not go into microplastic because it's in shape. It's for a while and it's not break. So it's kind of contained somehow, because the problem is there's too much plastic. So problem number one, we need to stop it. But we need also to kind of contain the plastic everywhere so it doesn't go and interact in a bad way with nature. So that participates a bit to that.
So as a follow-up, because you were saying you use kind of the same material together, how difficult it is to sort the plastics for recycling so that they are of the same material? Like if you go to a landfill, you're going to get so many types of plastic that you cannot really use in your art. But
okay. We don't fight landfills. Huh? We fight easier wars. But the fact that
what is the source of the material you get?
We've got several. We get the easiest one is when it comes from an industrial that uses plastic and has a lot of failures. So we get these failures. Well, that's very clean, very easy. But one of the things that help us is the density of polycarbonate, because it often comes with other plastic, but it's one of the rare ones that sinks. So we put everything in water, which allows us to clean it and also to separate it just by flotation. I mean, like one is burnt, and most of them are burnt, and one is polycarbonate is directly sinking. So we use that a lot, which makes us, of course, use water, which has a downside, but it's relatively efficient as a way of parsing.
Okay, I'm going to move to our audience's questions. I think the first question is from Muhammad to everyone. How can a foam house resist the wind load? Well, I think this question is addressed to you.
Yes, foam houses without frameless foam houses, yes, they can resist load. And in some calculations, they can go up to, in my calculations, I don't know others, they can go up easily up to 2 stories. They can take wind load if the thickness is acceptable and if it was also taken care of in the method that I showed.
Well maintained and well built.
We are having a deflection. Also, deflection due to wind will have to be added. That's easy. But it should take wind load. Yes.
Okay. Another, Guillaume, I think exposure to ultraviolet radiation can cause plastics to degrade, reducing their strength and durability over time. What measures are taken in your work?
But yeah, I don't control the material, so I just get it, but because it's UV resistant. So there's also some UV blockers in some of them. I believe there's some in the headlight for the cars. We have different grades, and the one from the water bottle is food safe, not in France, by the way. The only country in Europe that decided that there wouldn't be any polycarbonate water bottles, and no, also for the what do you say, for the babies, when you heat up the milk, it's not polycarbonate anymore as well in France. It's the only one who decided this, but I think it's wise. I mean, it's a good thing. It's good to recycle polycarbonate, but not probably the food stuff with it. It's not good. So it does it on its own, and we picked it up for that because we wanted it to be resistant, and somehow it's also Class B for the fire, so it doesn't burn on its own. And this is why we're able to do furniture for public space. So they can take the heat and they won't burn away, and they can be under the sun, and they would survive that. Probably the surface will change. It happens maybe to your cars, but a simple polishing or heat up will take it back to a glossy state.
Okay.
So I don't have also a very long experience. It's been just like 4 years we're painting with polycarbonate. I cannot say I've put benches for 30 years on the street. We will have to meet each other in 25 years to know that.
Okay, we'll have another meeting in 25 years. So to answer the question, you're using polycarbonate that are innately resistant to UV and also resistant to temperature. That means they do not burn on their own. They resist, they melt, they do not.
Yes, they do not self-combust. And in fact, the experience is that if someone, we had the experience because we have some furniture in public space, so someone who was bored, etc., tried to light it up. But so you need first a long time because we do massive objects. They are 12 millimeter, and one of our bench is usually like 80 kilos. So it takes some time before you get to a good temperature. And to get liquid, you need to get above 250 degrees. So it takes a lot of time. And what you get is a drop of liquid, which usually falls on the guy who's trying to lit it, which stops the operation directly. And the material is not combusting itself if you don't put a flame and a lot of energy to burn it. I mean, you need to really you would really need to do it. So that kind of stops the.
Okay, we have a question from our audience.
Hello. We as an engineers, we see the uniqueness. Guillaume, as an engineer, I really value the uniqueness of the plastic material in terms of these stands that we saw that maybe they are impossible to do or very difficult to do in the regular materials such as concrete and steel in terms of shapes, in terms of colors. But while I want you to share with us the uniqueness of using plastic in the concrete with mixing with the concrete, where I remember that we had worked on a project together where we used some fibers within the slab, substituting the steel reinforcement, and we used a slab for a lightweight slab, and we didn't have the capability at that time. We have some restriction, and we used the plastic as a reinforcements inside the structural elements such as slab. And I think this is unique, where a lot of engineers would be put in a position sometimes where they need to, they cannot afford to put heavy structure. And I think the plastic reinforcements is a good solution for that. If you can share with us this.
I think we tried this in a villa. Where is it? In Sousse. But it didn't work anyway, because the client didn't want it. Nobody could construct it. Nobody. Actually, we were thinking about lightweight concrete reinforced with some rope-like material. For a roof where the deflection is not very important, it may work. It's only a gabled roof, so it may work. But in slabs, I don't think it will work because the load is high enough to make deflections. For a gabled roof of that span, when we had I-beams below, it was okay. This is my answer.
I would like to add that we really pay a lot of attention in not mixing this kind of material, because after you cannot recycle anything anymore. So we are very, and that's why we take also this challenge, and we're not doing this shape because we right, what we did is that we developed first the machine and the process, and we are trying to create stuff within the lines of opportunities of the material. So it's more guided by the possibility of the machine. We call it emergent objects because they come because we would not have been able to do them if there wasn't this machine and this system. So this is more an exploratory way of doing things. It's more by the force of proposal and the creation rather than, so it's a completely different attitude probably than engineers. That's why I'm an architect. And that's how it's guided through the system. But it's a good mix. I like it's a good mix, and I like the conference, the fact that it's not monolithic and just one way of thinking, but that we mix both and we divide it in two, and the encounter of the two ways of thinking and of looking at stuff is quite interesting.
Because you are an architect and you are mostly interested in environment and these things, I am an engineer. I'm interested more in and stresses, and that's why we have differences. But we shouldn't be actually. Actually, we should complement each other. That's what I think. But we have to understand each other.
I think the main problem with the plastic being used in reinforced concrete is its properties to be elastic, and that doesn't help with the concrete because the concrete needs something that is not elastic to keep it together because tension and concrete doesn't work very well. So I think to address your question, I've read some research that was done with carbon fiber reinforcement that is lightweight and that actually can withstand a lot of tension without elongating. That can be used steel in locations where you have high corrosive environments because steel in that case would deteriorate the concrete. So I'm not sure if this addresses your question. Correct. You can, yeah.
Yeah, but we have to understand that carbon fiber is not plastic.
No, I know. I'm just saying as an
one,
alternative, not to compare it with plastic.
Very strong. And
Exactly. Can we see the questions on the screen again, please? I think we lost them. I think there were more. There are more questions. Okay, so first of all, thank you all for this amazing hard work from insightful information. I have two questions. Are the material used for such volumes made 100% of plastic? And what might be the long-term effect of those volumes exposed to high temperature? So,
actually, I have shown an Ashby chart showing versus temperature. Maybe this is the answer for the as long as we are these temperatures as an ambient temperature, I think we are still okay. The plastic will yield and creep also, not only yield, but there is a long-term deflection. And this is what we should take into account. And this is still under study. Actually, we don't have codes for it. But even if we don't have codes, engineers have used concrete for 70 years before the codes started. So why not? We can still use plastics without a code. I hope one day we'll have a code and we'll be more, we can understand ourselves better. But the answer is that as long as we are And this Ashby chart, I didn't get it from anywhere. It was from MIT. I think it is one of the best references I can think of. So I hope it is okay.
Okay, so to answer the question, are the material used for such volume made 100% of plastic, Guillaume? Your answer is, I think you said the connections were being used with steel or recycled aluminum or something.
Yeah, that is just the connector part is made from recycled aluminum and the screws are steel, but the rest is 100% recycled plastic, even to. And it's, of course, plastic, it's under the area that Wael was mentioning, which is we too much. So for the moment, anyway, our structures are more for temporary stuff. So we are kind of not completely concerned with it. And when we do a permanent things, it's more like furnitures. And indeed, the thickness we are using is far exceeding by far. So we have a great safety level compared to that. And I mean, they're really well. I mean, as I was saying that the helmets, I mean, the part where you can see through of the helmet of the astronauts are polycarbonate because they're at -250 in space. It has a great range. Before 150, there's absolutely no change in polycarbonate whatsoever. I mean, it's not becoming less strong or material. We know because we on the structure, on some of the structures that I shown, we 3D print the beam flat, and then after we have to heat it up again in order to thermoform it to an angle. And so we have to provide all that extra energy in order to
how much temperature, how much heat do you apply? What is the temperature that you apply so that you can bend it and reform it once it's formed? If you want to correct something,
it's above 200 degrees to do
above 200 to get some flexibility in it. So it's in its rigid form. It doesn't change between -200 and +150.
Frankly, until 150, you see absolutely nothing. I mean, like it's 150 and above that you start to be able to do something and to manipulate it.
Okay.
To references, most references below 140, it will never melt. All references refer to this.
Okay, so 140 is
probably
okay.
Our plastic is the recycled one. We sometimes don't know how many cycles it got. It's a bottle, it's clear. It was fresh. It was because it was food grade, and then it's the first use of this. But sometimes we are getting plastic which has lived a lot of adventures. And once we had a problem, there was some contamination with oil. And then several weeks after printing, we got some cracks which appear because there was at high heat, there was some reaction with the oil, and that creating real problem. So normally when industrial use recycled plastic, they use a fraction, let's say 5 to 10% maximum, because this is what they can lose in strength in what they do. It's still being at security. So how we deal with municipalities in France which are buying our furniture to put them in public space? We're telling them, okay, we took the decision of using 100% recycled plastic because we don't want any more fresh plastic, and there's so much of it. We need to find a safe place for it and some use. As long we say, we guarantee it for 3 years against this kind of things that would happen during the life of the recycling that would affect the property of the material. And they accept this. They accept that it might fail during those moments. We will take it back at material price. We will print a new one and we will replace it. So with this deal, this strong will is acceptable, especially in France, because it's very important. They have, I mean, every municipality has guidance, or you say direction from the government on how they should spend their money, and it has to be local, it has to be recycled, it has to be recyclable as well. It has to have a low carbon footprint. So we use little energy. We use a local plastic for local demand, and so it's within those things that you get when you have a call for a bid. That's how you get a grade and you get a contract, and so that's how we somehow succeeded into about every bid we participate, because we have a very high grade there. But there's a deal to be put, and everybody has to be aware of what we are doing.
Okay, going back to your comment about getting the contaminated plastic that caused structure. When you get your material, your recycled material? Do you cut them as chips, or do you kind of chip them yourself? You cut them into pieces,
Yeah,
and do you actually clean them? Like once you've learned that they could be contaminated, do you do the process of cleaning them before you put them in your 3D printer, and what temperature to actually form them?
250. Yeah. We get it in various. I mean, we have to. It's really like an animal that needs to find its food around him. There's a word in English for that. Kind of a harvest. So we're always on the lookout and it comes in different places, in different forms. Sometimes already it has been flaked. Sometimes it's already really pelletized, which is rare. And sometimes it's really the object itself. And sometimes it's even attached to something that we need to cut, the car lights. We often need to cut some part of it in order to use the material and to clean them a lot. So we get a bit all the conditions. In France, though, we really found people which are specialized and are doing it for us, and we get it really completely clean, passed, etc. So but in Lebanon we have the full chain in order to clean, to crush, to pelletize, and to do all this, including the coloring and stuff.
Okay, so another question. Plastic is viscoelastic. Its response. Oh, sorry, I missed a question from Saeed Filali. Does plastic dissipates energy in case of a seismic action? So I guess, well, this is for you. This is. Oh, so somebody answered the question. Let's hear what they had. Plastic is viscoelastic. Its response is time dependent, so it does dissipate energy as it goes through a hysteresis loop. Whether it dissipates as much as steel when it plastifies is related to context, quantities, and history of actions. Would you like to say?
I agree with this very well. Yes, I do. Yes,
Okay.
I do agree with this answer. I don't know who answered it, but it's a good answer. Yes.
Okay, so somebody asked, we have other questions?
The thing to notice is that it's our structure are very lightweight, so they don't have a lot of self-weight that pushed around, and also as we cannot really print very long elements without having problem with what I was explaining, that some part would be cold and some would be hot, and then there would be some deformation. We do it with assemblies. So we have many joints, and we have a lot of flexibility in the full system. When I was saying at some point it's a bit more like a fabric, there's so many nodes that it's somehow a kind of a fabric. So there are a lot of flexibility inside. So anything seismic would more like a bit, and then that would be it.
Let me add something here. Plastic is very light, and foam is even much lighter. So really, we will never have a problem with the seismic. We will have problem with the wind load, but not seismic load. Seismic load is very little because it is directly proportional to the weight. So we are not going to have any problem in seismic. Actually, the most important thing in such kind of structures would be how to tie it down against wind. So I'm not really concerned much about the seismic because it rarely happens. It happens.
So if we're talking about structures completely built out of plastic, I
Yeah.
have a question for you, Wael. During your presentation, you mentioned that the world produces around 300 million tons of plastic per year.
Per year, yes. That's what it says.
Right,
in
based on the
reference.
statistics. Do you know what percentage gets recycled and what percentage actually gets thrown into landfills or into the sea? Because we know there are entire islands of floating plastics in the oceans.
No, actually, I have no idea about it, but probably he will knows better. But I think most of it are not recycled, and we are having problems in microplastics.
Yeah, microplastics in the sea, I think it's a big thing.
I think the design part and the architecture, etc., are taking more care of this. I think I find them a bit more reactive than the engineers, if I can make a critic. It's a bit slow, huh? It's because of course it's the industry, the business, etc., etc. but we can. I mean, one of the problems is in recycling is it's mixed. So that's why I was talking a lot about making first identify them very well, then don't mix the things so we could reuse it, because if it's contaminated with something, it's a problem for me to reuse it. So that would be one thing. After we need to find other solution. I mean, recycling is the last. You know, it's repair, reuse, and recycle come the last one of the solution. So it's not optimal. But we're trying to make it through, and it's doing a little part. We are working on other material. So we 3D print also with clay. We carve wood with robot. We are working a lot with recycled paper. So recently we did a chair, which is and some furniture, which is made from recycled paper using flowers from rice and wheat as a glue. We put inside nutrient and seeds. So you've got a chair that could be indoor for a few hundred years, but if you trash it outside, then it would melt away in the winter, and in spring, there would be trees that would grow. So we will use this capacity of human to pollute to help the planet. So we can return those things. So creative thinking could be used into this, and because there have been a lot of bad decisions. I mean, like in architecture, there are plenty of very bad ones. Mixing gray water with dark water. I mean, one can kill someone because indeed there's Ebola, for example, among the 400 things that can kill intestine. Why mixing it with other water that could be recycled in a snap? Why do we have to put everything in the same drain and make everything mortal? That's completely stupid decision. We need to reverse those things, think again, and divide those tubes and do it differently. Plenty of wrong decisions were taken, a lot by engineers and some by architects. The more responsibility, the more.
There's
And,
actually environmental engineers that wouldn't agree with you. That's kind of their role, is to make sure that the other engineers don't set up.
Okay, I thought that was those were lawyers. No, but that's it. There's plenty of decisions that somehow our look at things is changing. You know, Scotch tape 20 years ago, you thought it was something very interesting. Now we know that it's two materials that forbids it to be recycled completely, and it's completely stupid. And there are tons of hundreds of millions of tons which are produced, and it's a wrong thing. Now we see it as wrong because we step back a bit, and now we need to invent something else. So we need to rethink those things, because I mean we were carried away a bit too much with the strengths of globalization and the heavy industry. We've been eating up the planet to create things which are not durable, and now we need to look at things again and try into other solutions. And this would probably go through some creative thinking, and that's why when we meet the knowledge and the way of looking at the world from the engineers with some more creative, more intuitive people, it could eventually lead to new forms that would respect some basic things which we need to be in a sustainable world. I mean, and to not burn the planet away.
Okay, one last question. You want to say something? What? Go ahead.
Something about what he said. It's. I think he is right by not mixing materials, because if the material is hard to recycle, but there are other ways to make composite materials that can easily be detached and then recycled. So in that case, we can have both benefits. We can, for example, if I get a small beam of plastic, but I reinforce it with the top steel and the bottom steel, it will be much, much stronger than what is usually. Exactly. Not only that, but I like to also add something that was mentioned in the presentation. One of the things that if we have a beam or we have a sandwich panel, on top of the sandwich panel, are building a house, a small house. We can't make people walk on the sandwich panel. We have to put something, a kind of a plywood, a kind of a plywood plus PVC tiling, something to make them be able to live in. So if this material can be chosen in a way to be in composite with the plastic, it will really help them also. And it is detached.
So my last question before we end today's webinar. I understand that almost all your creations are 3D.
It's all digital, but some is additive and some is subtractive. So we carve wood away, for example.
Okay. So following up on this question, I was watching a program on National Geographic the other day, and they were showing this lady in Africa who's using plastic recycling, like from landfills. So all kind of plastics all mixed together. They're melting them and creating from them tiles that are being used on sidewalks. I don't know if you've heard of these, and I guess can we go into mass production of these things when we can actually take away all these plastics from landfills and use them instead of tiles on sidewalks or in some areas, because you can actually in melting them, maybe it's easier than using them in 3D printers that actually needs more lean material to be used. So if you melt them together, then you can actually press them together and use them as tiles or something else.
Yeah, you've got less probably, I mean, less complex objects, which are also probably less useful. I mean, with less complex program. So there should be both. I mean, like the precious plastic, for example, which is the root of all those initiatives, is taking it mostly from the sea. When you start to mix plastic and to mix their melting point, it's true that it's a bit more complicated. So you would over melt some and then create a lot of gases, and then some would be almost not melt and etc. And you would get into something. It's the lowest point possible, but when we are at landfill level, anyway, it's better than just being at landfill level. Yeah, it could be. We should. I mean, it's a big war with a lot of fronts. I mean, like we should find replacement for plastic, so we recycle as much as we can and try to make sure the impact is limited and we contain the thing. So there's plenty of action. I mean, you cannot fight all the wars. We tried to do that one, which was kind of the ones as well with different material. I mean, mostly looking at for construction because we are architects. So, for example, we recycle the aluminum from the offset printing press to make material for houses. So, I mean, it's a bit like as we can through what we find in our environment. And we can talk about Ziad Abishaker, who's here doing it, getting whatever kind of plastic, and the very strong will of is not cleaning them because he doesn't want to dirty water. He decided this. So he presses them together to make boards, which is called eco boards, which really stink. I mean, it's really strong. I mean, like they're very, very strong. You cannot use it for an interior. It could be only for something outdoor.
I think he's doing manholes because the manholes were being stolen, and I think he was doing manholes as well, the cover for the manholes.
Yeah. So he's trying various, but there's still plenty of uses for this kind of material. He's doing also a box for shipping stuff because it's relatively lightweight and it can take various shocks without breaking. So what's inside is protected. So there are plenty of levels where to fight with. It's also an information war somehow. So somehow what is important a bit with us is that we manage to find those car lights. We put some fun color inside of it, and we create some products which are relatively happy and beautiful. And we are also saying in a way that future could be sustainable, and it's not about reducing everything, decreasing, and there should be some of that, but it's not only that. There could be also some new creative form, new object we've never seen. It could be exciting as well and still be something sustainable in the future. So our little war has this kind of condition, and we try to do good at it, and we try to go a bit over in scale from furniture to architecture. And that's a bit where we are. We don't fight all the fronts, but there are plenty of it. So I hope it inspired a lot of people to take one and to fight for it.
I'm sure it did. And thanks again, Guillaume and Wael, for your time and this excellent presentation. And thank you, Dr. Mshaileh, for hosting us here tonight. And thank you, our audience, for being with us in this rather longer webinar. Thank you, everyone, and have a good night.
Thank you.
Thank you.
Thanks very much.